Thank you very much, and thank you very much to the IOP for, first of all, organizing this great meeting and inviting me to it. I'm going to also, like the previous speaker, going to talk about light and matter, and I also going to talk about polaritons, so the different kind of polaritons. But my talk, as you shall see, is completely different. But before I go any further, I'm going to talk about magnetism, chirality, and other things that you can do by driving high amplitude phonons. And before I go any further, I just want to acknowledge my collaborators. You may have heard a version of this from Andrea. This is his group at Hamburg, of which I was a guest last time I was on sabbatical. And particularly, the most recent work has been done by our joint student, Paul Zhang, very talented student, who is now in Hamburg, spending part of his PhD. Okay, Prabhak, so I should acknowledge Prabhak, who's grown all the samples that I'm going to present. Right, okay, so structure property relationship. The condensed matter physics in the last century or so has been dominated by the idea that you can change electronic, magnetic properties and other properties of materials by changing some parameter. So that's an example my student came up with, the vanidates, the strontium version is less distorted, and then you go towards other composition and you change, for example, the valence, and you change the size, and you change the distortion, and you can change things from metallic to insulating, from paramagnetic to antiferromagnetic to ferromagnetic. So that's the story, at least a great part of condensed matter physics since the 1930s. So generally, many of these things entail some kind of symmetry breaking, which can be spontaneous or induced as you apply an additional parameter. You can change things by applying external pressure or changing temperature, applying magnetic field and strain. All these things, or indeed changing position, all these things are slow parameters. So you can change them on the laboratory time scale, but at speeds that are relatively slow. Can we achieve similar effects in the ultrafast? And of course, that would be very interesting for many reasons, both for application, but also for our fundamental understanding of these materials, and more on this later. So the field of ultrafast condensed matter physics has been going on for a couple of decades now, if not more, but a decisive technical contribution to the field has been due to the development of mode-selective coherent light controllable coherent. Mode-selective means that you can create pulses of light down to the mid-infrared and far-infrared regime, which are short in real time, of the order of less than a picosecond, and at the same time has a well-defined and tunable frequency. Okay? This has created the possibility of having a handle on matter that can address individual excitations that are coupling to light. Okay? So, however, you have here an electric field in the materials that propagates in the materials, and we'll talk about that a little bit later, and it's vastly oscillating, whereas you want to get some kind of rectified response. So you want to have a pulse of magnetism, a pulse of ferroelectricity, something that is not oscillating with that frequency. And the answer to this is the so-called basic idea of phonon rectification. So phonon rectification works a little bit like Lac rectification, right? So it's due to a nonlinear process and a nonlinear interaction of phonons, whereby you pump a single infrared active mode, and there is a structural and electronic distortion that is rectified along the coordinate of a second anamorphically coupled mode, which in centrosymmetric systems will be a Raman mode. So in a centrosymmetric system, infrared active modes and Raman modes are separate. So this is sort of a very cartoonish Lagrangians of the equation of motions of these two coupled modes. And the idea is that your Raman mode, I'll show this a little bit later, will couple to the infrared mode, creating a displacement in one direction of the Raman mode. So, and then when you have something, you have a distortion in your materials, or you have magnetism in your materials, you have something that has been turned off transiently, you can probe it typically in an all-optical fashion, but you can probe with X-rays, you can probe many other things in the ultrafast regime. Now, as I'll show, I'll go to the next slide. Okay, so this is a enlarged view of the same kind of toy Lagrangian, and this is the key coupling term between the Raman mode QR, the coordinate of the Raman mode, and the QIR, which is the infrared mode that you're pumping. This coupling is always allowed if the Raman mode is totally symmetric. Okay, so the so-called A1G mode, if you are in a center. So it's always possible to couple any Raman infrared mode with a Raman mode that is totally symmetric. This gives rise to a totally symmetric perturbation, which is rectified in the material, which is a sort of a weird pressure, if you want, weird hydrostatic pressure. So if you apply pressure to a material, you generally, unless you go through a phase transition, you don't change the symmetry. And this is a sort of a weird pressure. Right? You change the atomic coordinates in a different way with respect to pressure, but it's totally symmetric. Now, what is the effect? Okay, so imagine a system that might undergo at some temperature through a phase transition, and you have an order parameters, which in the high temperature phase will be parabolic, and the low temperature phase will have minima. If you pump in this way, the effect of this is to tilt the order parameter landscape in the paramagnetic phase and in the low temperature phase, the ordered phase, to change the height of these, or the depth of these potential wells. So in principle, you can have an ability to change the order parameter in the highly symmetric phase away from zero, so to create a non-zero value of your order parameter, whatever that might be. Or if you are in a low temperature phase, to switch between two different states. Right? So depending on the direction you're pumping, you can switch between two different states.
Component at twice.
There's still an oscillating component. So the Raman mode will have a rectified component and an oscillating. I'll show you some examples of what that means. Okay, so this approach. So that's the way people picture this approach, right? It has had a lot of success in driving metal-insulated transitions, manipulating charge and orbital ordering, switching magnetism, ferroelectricity, and even superconductivity, inducing superconductivity. And I have quite a lot of references here to this. But all of this has been at least understood in the framework of AG phonon-driven rectification. And where I come into the story is the following consideration. What is possible beyond totally symmetric mode? Can you rectify a mode that's not symmetric? In other words, can you break symmetry by that? Okay. So can you achieve a transient breaking of the crystallographic or magnetic system symmetry, and therefore, in the spirit of Curie celebrated principle, cella di simmetrie qui crée le phénomène, is symmetry, a phenomenon. Could transient phenomena emerge from this breaking of symmetry with light? So, can you activate ferroic order parameters, magnetism, electricity, or other parameters, chirality, transiently? Right? So that's the question, and the answer to it is yes. So if you pump in all the different modes, you can only couple. But if you couple to the degenerate mode, the mode that has two possible direction of the order parameters, that you can pump.
Normal से तो 3-4
then you can
4-5 दिन तो लगेंगे
a mode that is not totally symmetric. Okay? And in a way, the best analogy to this is the piezoelectric or the piezomagnetic effect. You apply a strain, and then the strain breaks the symmetry, and activates, for example, in the piezomagnetic effect case, it activates a magnetic moment. Okay? So the magnetic moment is created when you apply strain. And in fact, the analogy is actually much closer than this. Okay, so I'm going to talk about this example because it's really an exemplar case of what you can actually do. Right? So the idea is to create and to exploit this principle to create transient ferromagnetism by linear pumping. There is an effect known as the inverse Faraday effect, which is allowed in all symmetries, whereby you can create a magnetic moment by pumping with circular light. But pumping with linear light, and getting a magnetic moment is completely counterintuitive. But in fact, it is possible, and it's possible by the same principle that drives the piezomagnetic effect. In fact, cobalt fluoride is a very well-known piezomagnet. This is why we chose it as our first study. It's studied since the 1950s. And the way this actually works is the following. If you apply strain, this is a static experiment. If you apply strain, you create two different sites. So you have the cobalt fluoride is a collinear antiferromagnet with two sublattice. The magnetic moment is along the high symmetry axis, the C axis. The two sublattices become structurally inequivalent if you apply strain. And because they are structurally inequivalent, there's a different crystal field. And because cobalt's configuration allow an orbital angular momentum, for a component of the magnetic moment due to the orbital part, the two components will no longer exactly cancel out, and you get the ferromagnetism, having two sides carrying different magnetic moments. If you inverse the direction of the strain, so if you reverse the direction of the strain, you change the direction of the magnetic moment. And this is domain dependent. So if you apply time reversal, if you switch all the magnetic moments, you get the opposite ferromagnetic. So that's very neat. That was demonstrated in the 1950s. And can you do the same thing by light? Well, it turns out that the symmetry of the quadratic field that you create by pumping an appropriate infrared phonon, in this case, a degenerate EU phonon, is exactly the same, has exactly the same symmetry as the strain. So the idea is that can you observe a magnetic moment arising from pumping with linear light? And the beauty of it is that if you rotate the polarization of the light by 90 degrees, you should observe the opposite. That was the idea. Now, if you go into the detail, you say, well, okay, which mode then? There's more than one EU mode. It has to be a degenerate mode, you know. There are many modes, several modes that have the same symmetry, and each of them will produce a different pattern of atomic displacement and will produce a rectified when it couples to the Raman mode. What you can actually do in this case is carry out essentially frozen phonon calculation by DFT, whereby you displace this EU mode, and there are three EU modes that are being considered, and the blue one is the response, right? So the blue one is the response, and as the question indicated before, you see there's a highly oscillatory component, and I'm looking at it, there's a high oscillatory component, but it's also a rectifier. Both are. And the hypothesis, we'll talk about this a bit later, is that this oscillatory component is what produces the displacement along the Raman coordinate that ultimately coupled to the magnetic moment. So how do you probe this? Well, you know, there are well-established ways to determine whether there is a magnetic moment. The most obvious one is the Faraday effect, the rotation of the light the probe light as it propagates through a ferromagnetic crystal. There is also dichroism. So in the optical dichroism is enhanced near certain resonances. So we did both experiments. This is actually the setup. We did also test a zinc fluoride crystal, which is of course shouldn't have any effect on magnetic. This work was carried out by Diane Kidiza, who is now faculty at Cornell. And then you pump, this is the optical spectrum, and the optical sort of propagation of light in the crystal near a resonance is a very complicated business. Of course, you're exciting a phonon polarity in this case, which is very slow propagation in the material. So you have to take that into account to some extent. But in this case, what you would expect is that the effect, i.e. the signal, could be maximum by pumping with the pump along the 110 direction or the -110 direction of the crystal structure, and then the effect should reverse. So the sign of the Faraday rotation or the sign of the dichroism should reverse as you change the pump polarization between these two directions. Okay, so you should switch magnetism by the light polarization. Right. Okay. So I'm not going to do this. I'm going to show you this, which is the Faraday rotation. And this is with the two polarization of the light. And I'm going to comment on this in detail, but look at the time scale of this effect. Okay. So the time scale, the scale of the graph is 500 picoseconds, which is huge. Let me come back to it in a second. And in fact, we also use circular Dacres to confirm that we will not some kind of artifact, and this is the circular Dacresm again developing over time scales of hundreds of seconds. Now, this is profoundly weird and profoundly counter to the kind of dying feature that so remember, what we said is that we were pumping up the phonons. The pump pulse is less than a picosecond. Then these phonons propagate relatively slowly, but the lifetime of a phonon typically, of a phonon polarizer, is typically 10 to 20 picoseconds. So the whole oscillations in the crystal only last 20 picoseconds. Now you have here a response that lasts for hundreds of picoseconds. So it cannot be what we're seeing, and well, this is an experimental result. It cannot be due to the fact that there is an oscillating phonon field in the material. There's got to be something else that you have created. You have created some kind of recurrence in the crystal, which produces a Faraday rotation and produce Dacresm over hundreds of picoseconds. Okay, what that is not entirely clear, but what is for sure, you cannot understand this experiment in the kind of adiabatic picture, whereby you have a phonon field in the crystal, high amplitude phonon fields with no linearity, and then this drives the electrons adiabatic. It cannot be that picture. It has to be something. Okay, so just to confirm that this is not some kind of artifact, we measured that some sanity check is that the effect must be temperature dependent, must go to zero in the paramagnetic phase. It has to be maximum. Well, it's at zero temperature where all the spin where you have an antiferromagnetic phase. Remember, this is very magnetic moment, right? So you are imbalancing two sublattices, and therefore the two sublattices have to be ordered. That's what you would expect also for the piezomagnetic effect. Indeed, temperature dependence is there. You also can confirm that the effect is quadratic with the peak electric field because it's due to phonon nonlinearity, and the electric field will be proportional to the amplitude of the phonons you're driving. So the effect would scale with the square of the peak electric field. And also you can confirm that the effect is resonant. Okay? So the effect is maximum when you are in resonance with the 13.2 phonon that you're pumping. Right? So these things all represent sanity check that indeed you are what you're doing, what you think you're doing. One observation is that in fact the Faraday rotation is very large with respect to what you can get with static piezomagnetism, which is quite interesting. Anyway, what is going on? What you would expect is an effect at very short times, and in fact you can see a very short time effect, but then there is also a very long effect, which is much larger. So this needs to be understood. I didn't discuss the issue of phonon polarity and the way it propagates. It turns out in this case is perhaps not as important in other cases because you're exciting a degenerate phonon, so at least everything is propagating within the crystal, regardless of the polarization of the pump. It propagates at the same speed, which is about a tenth of the speed of light. But obviously, many systems, this is this kind of the photophysics within the crystal is a very important consideration to understand these phenomena. Okay, so let me just conclude on the magnetism. So mod-selective pumping has been able to induce ferromagnetism, at least in the optical probes that we can use. So the prediction, which is entirely based on symmetry, was actually verified. And the timescales are quite different from what you expect naively. So the idea that the Raman term acts as a driver with electron responding adiabatically is kind of difficult to maintain. Right. Okay, so I just want to talk about something else. So we talked about magnetism, but it turns out that this trick can be applied to many other things. Okay, so we already mentioned previous results on superconductivity and ferroelectricity, but there are two new effects that we have observed: light-induced chirality and light-induced ferroaxiality. I'm not going to talk about ferroelectricity because of lack of time, but I want to say something about how you can create chirality using linearly polarized, which is also kind of a neat trick, I think. And this is just scratching the surface. There are many more effects that you can create, and I'm sure you can detect it if your probes are sensitive enough. Now, understanding what's going on in the material and what is the response is much more complicated. Okay, so what is the general principle that you would want to do these experiments? So first of all, you can select the symmetry. So the effect that are allowed by symmetry, when you have this quadratic coupling, quadratic linear coupling between phonon modes and Raman modes, is quite simple. You just look at the tensor that become allowed, and so you can select the symmetries of the crystals based on the effect that you want to obtain, based on simple tensorial consideration. For example, if you pump with linear polarization, you will break higher order axes order than 2, and you can go from a point group symmetry that is non-polar, non-chiral, such as 4-bar, to a polar and chiral symmetry like 2. Okay, so you expect from symmetry consideration to get polarity and chirality. So you have to select the appropriate materials based on various consideration, select and model phonons. Again, some of this can be guided by frozen phonon calculation, at least to see that there is a significant nonlinear response, and then select your probe, typically all optical or X-felt. Okay, so this experiment was part of the thesis of my student, and is concerned with a materials called boron phosphate, which crystallizes in the I4-bar space group, which is non-chiral, non-polar. Okay, and also it's an insulator, which is good because it's good for pumping. Also has a so-called ferroaxial point group, which means that that produces a coupling between polarization and chirality. Polarization and chirality are coupled through the crystal structure. So the expectation, as I mentioned, is that the pumping in the XY plane would reduce the symmetry from 4-bar point group symmetry to 2, which is both polar and chiral. So in fact, the original aim was to observe ferroelectricity, which is ongoing, but we clearly observed chirality. And the probe, obviously, for chirality is again optical. This is more or less a reproduction of what I've said before. You have to consider the coupling that is possible, and if you want to use a degenerate E phonon, because that enables you to break the symmetry. You wouldn't be able to break the symmetry with a non-degenerate phonon. In this case, you couple to a B phonon, which is the phonon that is responsible both for ferroelectricity and chirality, and you can select here in the curve. To the right, you can select the correct mode or the more promising mode by looking at the nonlinear response and making sure that the B phonon has a rectified component, as I explained before, as well as an oscillatory. So then you do the experiment, which is the interesting part. And the way you pictorially imagine it, there are different fragments of the crystal which have opposite chirality, so different structural motifs, and they become inequivalent, so they create net. And the net chiral, the sign of the chirality should switch by switching the polarization, pump polarization by 90 degrees. So I'm just want to show one caveat. So there's an additional nonlinear effect in this particular case, which is birefringence, because you are breaking the fourfold axis. The crystal will become birefringent. So for an arbitrary probe polarization, you get an optical rotation due to the birefringence. You need to be separating the two. And the way you separate is that the birefringence averages to 0 over all the polarization of the probe, whereas the optical activity doesn't average to 0. So we observe clearly optical rotation due to birefringence, but if you average the signal, you get a net chirality signal. And the net chirality signal, which is the average of the rotation over all the possible probe polarizations, is positive if you pump in one direction and becomes negative if you probe in a direction that's rotated by 90 degrees. I'm at the end of my talk. I just want to have a couple of conclusions before I leave you. So mode-selective pumping can indeed generate magnetism and other ferroic properties, including, and I mentioned ferroaxiality, which is interesting because ferroaxiality does not have a conjugated field, a static conjugated field, whereas you can manipulate that with light. These are generated on ultra-fast timescale. But much progress still needs to be made, both theoretical and experimental, to understand what really controls these phenomena beyond the naive adiabatic picture. That's it. Thank you very much.